Well, the probability of being 21 is not the same as the probability of sending more than 99 texts or something. Why should they be the same? Right? I mean, to be independent, one can't affect another one. Their probabilities are just sitting apart from each other. Why should they be the same and that means something? You know, so the probability is I'm gonna flip a head is 50%, and the probability of the person coming down the street is male is 50%. Does that mean that they're somehow dependent or independent on each other? No, they're two separate probabilities. You have to see how they interact with each other. Yeah. Any other questions from the quiz?
How many points did you take down?
4.
In number 1.
Because 4 people.
What's the main?
Point.
And I had the word in there. One of the main things to get from chapter 4 is what does and basically mean?
Multiply.
Multiply. What does or basically mean?
Add.
And I'm going to reference that from now on without any mention of that reminder of that. I'm just going to say, remember, and is multiply, or is add. There you go. Keep going. We've already done that. We did that when we did the binomial. If I have 5 people and I want to get one left-hander, the first one could be left-handed, and the second one not, and the third, and that's why we multiply. That's why we put them together with exponents, because that's the algebra for multiplying similar things. And then where'd that number in front come from? Adding them, because I could do it this way, or that way, and or basically means add. So those ideas will be used a lot in the rest of this semester. So any other questions as you're looking that over? Oh, cool. Bam. Okay. So again, do not give up hope if you got a very low grade on this. All right? I know it counts double, but it's like any other quiz. You can make corrections on that to pick it back up. Okay. Any questions from homework before we get back into new stuff in chapter 5? Anybody still not get a handout from chapter 5? The stuff for the XP of X stuff?
April 12th it says.
April 12th? Oh, after spring break, right?
Yeah. We only really had.
5-3.
We just have a designer, so this part exam to
This is from section 5.2. We've gotten up to 5.3 in the lecture. Okay.
That's a lot of chapters.
Oh, okay. But it's just a review, I think, from chapter 4.
Oh, really?
Yeah, I'm not sure. I haven't studied it. The standard deviation and all that. It's like kind of review.
See if I can
This is kind of hard because
find myself.
There's no standard deviation. And here it's like it's very simple. That's helped a lot. It's close.
It's another thing. If it helps out the other classes, you remember that.
Exactly. Yeah.
All right, guys. So let's do a couple of example problems to kind of remind ourselves what section 5.3 was all about. We put the formula down on the board last time. Guys. So the formula very often gets in the way. Part of it really freaks people out, but that part is really just trying to say the rest. So the official formula for these guys. And the part that really freaks people out is this part right here. Besides my q's, that look like q's, the n minus x part freaks people out. But the idea behind this was, I'm going to have this many successes. The rest must be failures, and that's how math does the rest. Right? The whole thing minus how much you've done so far. That's the rest. You saw that back in algebra. Remember, the dude had $30,000 and he wants to put part of it in this account, part of it in that account. One was X, one was 30,000 minus X. The rest. The whole minus the part. So in this case, N is the total number of what we call trials. So a trial could be looking at a person to see if they're left-handed. A trial could be rolling a die. Whatever this is that you keep repeating and repeating, that's a trial. X is the number of successes. P is the probability of success. And Q is the probability of failure. I like that. I'm so lazy that I can't write 4 letters out. We'll put little dittos. Oh well, too bad. So let's do a problem. Let's do an example of this to see how it works. Yeah, what does that C refer to?
Choose.
Good, choose. And that whole part of the equation, the NCX, I really desperately would love it if you guys could. What happens in math all the time is you get an idea, then we do the formula, and then you forget how the idea attaches to the formula. Like you forget why that's there and why is that there. This was just because.
Oh, that's a C. That's a C.
That's a C, yeah, sorry. So that's choose. And that's really like if I had 30 people and I want to choose 7 of them to be left-handed. What this does is it tells me how long the list would be. All the different ways to make that happen. Right? Each of them are going to look like this. So for example, if I had 30 people and I want the probability that 7 of them will be left-handed. And remember, left-handed was 11% chance. So it's probably you're not left-handed. 89% chance. Okay, cool. So that's the little summary I would do for any binomial problem. I would figure out what's N, what's X, what's P, what's Q, and then it becomes a plug and shove. But each of these is going to, how many of these am I going to want in each case? How many successes do I want in each case? Because it could be the first 7, or the last 7, or the middle 7, or the first 2 and the last 5, or the first 2 in the middle, 3 in the last 4, 2, whatever adds up to 7, right? You with me? There's a million different ways, not a million, but there's a lot of ways to do it. But they're each going to have how many left-handers?
7.
7. And how many not left-handers then?
23.
Yeah, 30 minus 7. 30 minus 7, the rest. So in practice, this piece is easier than it looks. For some reason, this really confuses the hell out of people because it has to look ugly, but it's just the freaking rest. So up here's got to be how many ways there is to do that. Like I said, you could have the first 7 and the last 23. Or the first 3 and the last 4 and the middle 23. All these different ways to combine it. And how do you do that mathematically? 30, choose 7. That tells you how long the list would be. Cool. So how would this look in the calculator? I don't know. We'll never know. There you go. It's a question for the ages. If you need a bar calculator, I got 4 of them up here. Such a nice. Oh, no. Did you get yours? Oh, no. Cool. While that thing is deciding to start, anybody else not get their quiz back? Okay, cool. Oh, good. here's how it would look in the calculator. 30. How do you get to choose? Good. Math. Probability.
PCR.
Third option, yeah, and this is all on that calculator Bible you got the first week of class. 30, choose 7 times 0.11, that's success, and I want 7 of those, times 0.89. Again, you don't have to put parentheses in there, I don't think. To the rest, the 2030. Okay. So then there would be almost a 3% chance that out of any group of 30 people, exactly 7 of them would be left-handed. Now, just to get to the more practical question, you don't often want to know exactly 7 left-handers. Because let's say you're trying to set up a classroom. And you're like, how many left-handed desks should I put in this classroom to make sure I sort of hit the right number for in general? So let's say that every classroom's got 30 students in it. You with me? And I'm saying, how many, if I put 5 desks in there, will that be enough to keep people happy, right? So that would really say, out of any group of 30, students, what's the probability that there will be at most 5 left-handers? I desperately want you to be with me on this. Does that make sense? Does that sound like a good, practical question that you want to know the answer to? I mean, obviously, from experience, I wouldn't put 28 left-handed desks into a room and have 2 right-handed ones. That's kind of stupid. I would have a lot of students come and complain. So the whole point here is to try to keep, to know ahead of time what's a good average, what's a good number to put in, to overall hit the right number for each classroom. Some I'm not going to have enough for, some I'm going to have too many, but oh well, I've just got to live with that. But I want to get close. What is the difference between this problem and that problem?
You're choosing 5.
Besides, one's got a 5, one's got a 7. What's the big difference? Which one is going to involve more work? Yeah, because what's at most 5? What could be at most 5?
Between the 30s.
It could be none, 1, 2, 3, 4, or 5. So there are 6 things that match that. You with me? At most 5 means 5 or less. So you'd have to do this formula how many times? 6 times. That sort of sucks, right? You guys with me so far? Yeah.
Can't we just get the same formula and get 5 minus that? Or we can't do that?
Probabilities have to add to be 1. So I can't take 5. That can't represent a probability. 5 can't represent a probability. There's no quick way to do this. Trust me. There is, but it involves letting the calculator do the work for us. I'm not going to give you a lot of problems that obviously have just a bunch of busy work. Could you guys start to set up? So it'd have to be for these. Probability at most 5 would be probably 0. Probably 1, 2, 3, 4, 5. What would this one look like if I wanted to set up the formula? How many people do I have? 30. How many do I want to choose to be left-handed?
0.
None of them. You're the probability of no left-handers. So I have 30 people, choose none of them. So how many of these do I want? None. So how many of these do I want? 30. Plus, or, right, you can do it this way, or this way, or this way. This is trying to be a P, by the way. How would I set up the one for this?
Same way.
Same way. I got 30 people. I can't write that one. I want to choose how many this time? 1. So how many of these do I want?
29.
1. And how many of these do I want?
These 29.
The rest. So it wouldn't be that difficult. It wouldn't take that long. Right? You sort of with me? So just to really hammer this home, do that. Keep going. Finish it out. Get the whole probability. I'll wait. Call me over if you need some help. I would first set up the formula for each one and then plug it in. It shouldn't take crazy long. And then I'll show you the shortcut after you do that work.
You're just trying to give us heartburn.
Let me show you a little trick with the calculator that'll make this quicker. I would just write out the first, 4 decimal places here. If you hit the second enter button, you can go up and just really quickly make a 0 a 1. You see what I'm doing? Just go up and change the things you need to change. You can do it, Jeff. There you go. See, so that's probability of 0. That's the probability of 1. You guys see that?
No.
Let me do it again. So you guys with me? That's the probability of none, right? Right there. 0, 11 percenters, 30, 89 percenters.
You got the answer, bro?
Right, no left-handers, 30 non-left-handers.
89.5%.
Almost.
If you hit second enter, and I want to keep harping on the second enter thing because in this class we're going to hit these kind of large formulas where if you put one thing in wrong, that's so going to suck to try to retype that. You don't have to retype it. Hit second enter, it brings the whole damn thing back up and you just go up to where you made a mistake. In this case, it's not a mistake. It's just that I don't want to go through the steps of putting all this crap back in because most of it's the same, isn't it? Here's probability of 0. Here's probability of 1. How do I make it the probability of 2? 30 choose. Shit, I lost everybody. All right. So we have to understand the formula by itself. And now I'm trying to help you with the calculator, how to make it quick to plug things in. So do we all understand the formula? First off, if I would have 2 left-handers, how would I set up the formula? It would be 30 choose 2, because I want 2 left-handers. So how many .11s would I have? 2, because I had it squared, because I want 2 left-handers. And you see how the formula is kind of repetitive a little bit, which is nice. So how many .89s? How many non-left-handers would I want? 28. So just go change those
So you add
things.
all these up, right?
Yep.
Make this a 2, not a 23, Jeff.
My calculator.
Make this a 2.
Yeah.
Make that a 28.
I love my 89, dude.
Right.
Sometimes. Sometimes. I know how to do it.
So what I'm getting so far is this was .0303. This was .1124.
Pretty damn close. Pretty damn close.
It's okay. So,
Probability for 2 was .2015.
Mine goes out like 26 things.
You with me so far?
Yep.
All right, keep going. 9345. This is good. This is good practice for how the hell do I set up this equation and how the hell do I plug it in my calculator. Can't do either one of those or both, you're screwed. Not sure where to put you. So let me just catch up to you guys. So to get for 3, make that a 3, make this a 3, and make this 27. 2, 3, 2, 4. So for 3, it's 0.2324. For 4, what is it?
1939.
So for 4, I hit second, enter. Go back up. I can make this now. I want to choose 4 people to be left-handed. So I want 4 11% people. And 26 of the rest. Interesting. I do have an alternate reason for this, and don't think, oh, this is great. We're getting a bunch of freaking numbers for whatever reason. Something's already happened that's very interesting. Anybody got the 5, the 5th one?
Yeah, it's 0.1246. 122.
1, 2,
46.
4, 6. Okay. Even with that, I mean, we can keep going to 6, 7, 8, 9, 10, 11, 12, up to 30, right? As I get closer to 30, what do you think should happen to these probabilities? Exactly, because there's only 11% chance that somebody is left-handed. In fact, if I have 30 people, how many people would you guess would be left-handed? What's the percentage of all people that are left-handed in the United States, actually? 11%. So if I have 30 people, 30 randomly selected people, not 30 people shopping at a left-handed store, but 30 randomly selected people, how many of those people would you expect to be left-handed? 3. Let's round it down, because the 0.3 person scares me. Right? So I expect 3. What's the highest probability we've seen so far? Which correlates to how many people being left-handed? 3. Shit. You guys see? So I expect 3 people to be left-handed, don't I? If 11% of people are left-handed, and I have 30 people in a room, randomly selected, I'd expect 3 of them. What does that mean for the probabilities? What should be the highest probability? 3, because that's the one I expect, right? And of course, as you get away from 3, it should go down. That sounds like some of these might look normal. Doesn't it start low, go high, go back down? This one's going to have a big-ass tail, though, going all the way to 30. You with me? Sort of? Okay. So how do I get, so I'm pointing out a few things at once. How do I get this probability then? At most 5, I would just have to add all these up, right? So could somebody do that for me?
0.8951.
So all these together, what now? 8?
8951.
So there's always the concept, the work, and then do you understand what the hell you just did, right? So the concept of this formula, the work of just doing the formula, now we did all that, do you understand what that really means? How many people, what percentage of the people would I expect to possibly be upset if I put 5 left-handed seats in a room then?
89%.
This is the probability that at most 5 people will be left-handed. So what's the probability that more than 5 people will be left-handed? 1 minus this, right? 10.5% roughly. Is that an acceptable percentage of being wrong? Is that acceptable? Well, it depends. Are left-handed desks more expensive? Do I have to pay more money for them? Probably not. They just turn the stupid thing around, right? Should be more expensive. So I'd rather err on the other side possibly. I'd rather put maybe 6 or 7, so I don't have 10.5% of the people coming to me and saying, dude, what the hell? Right? You guys kind of with me here? It's very similar to the airlines trying to figure out how far can we overbook a flight and still be good PR-wise? What percentage are we okay living with of people being upset that they got bumped because we overbooked every damn flight? They have people always looking at the statistics and kind of recalculating, yeah, you can go this far, you can go this far, you can go this far. You with me? A little bit? Yeah.
So when you add them all up and you get that 0.8951, what does that number actually mean?
So that means 89.5% of the time. So let's say you have a lot of classrooms, and every classroom has 30 seats. 89.5% of the time, you'll have at most 5 left-handers in there. So what percent of the time will 5 left-handed desks not be enough? 10.5% of the time. Can you live with that percentage? Maybe yes, maybe no, right? Do you already have a bad reputation with left-handers? You probably want to go a few more desks up. Right? So if I added 6 in there, you can add a 6 on top, and then you can see, well, what percentage of the time would I have people upset at me? You kind of with me? A little bit? Well, a few of you guys are. All right. So it's always difficult. That's why people don't like statistics, because not only do you have to get the work down, and I'm not trying to make it sound really difficult, but this is what people don't like about it. You have to get the work down, but you also have to be able to interpret what the hell you just did. And this is a very practical, real-life situation. That's exactly the math that is used currently in situations like I just described, with seats on airlines, those kind of things. How wide should airlines be so they have people not complaining that it's not wide enough? Well, it all depends on what the current butt width is, right? That's always changing for America. You with me a little tiny, you can see this here? Okay. Are you guys feeling okay about the nuts and bolts? Because you set these formulas up and calculate them. It's always that part D. You know, I'm referring to homework. Part D. What the hell is this just mean? And a lot of people just kind of, maybe he won't notice if I just leave that off. But it happens. Okay. Oh, so here's the shortcut. So if you go to, now obviously, anytime I show you a shortcut, I'm big on work. You still got to show me the work. And showing me the work does not mean telling me what buttons you pressed. That's not showing me the work. So if you had a teacher in the past that allowed you to do that, that's great for them. It's too bad for you right now. You got to show me the work. This is how you check yourself. Let's do the one we just did right here. Since that number's right here. You with me? So this was the probability of having 4 left-handers. Here's the shortcut. You go to second, vars. And see above vars it says DISTR? That's for distribution. Because what distribution am I in right now? NPQ, I'm in a binomial distribution, right? That's a binomial, 2 outcomes, P or Q. So where do I want to go? I want to go to, and these look interesting for later.
0.
No? Well, it might be. It depends on your list. So you got 2 options here, don't you? Now again, your list might be differently numbered than mine. But if you scroll down, you find binomial PDF and binomial CDF. And those 2 are explained on the Calculator Bible, but let me just tell you, P means particular, C means cumulative. So if I use this guy and put a 4 into it, I'm going to get the probability that it's exactly 4. If I use this guy and put a 4 into it, I'm going to get the probability that it's 0 up to 4. It's going to add those together for me. How are we doing so far? So just to double check that one I had on the screen, that was exactly 4, right? So I want to use PDF. I want a particular value. I want 4. So let's try this one. So A, for me, you want binomial PDF, for those of you playing along. Now here's the inputs. Here are the inputs for both P and C. So you're going to put in there N, P, X. And of course, the calculator does not need to be told Q because it's a freaking calculator. You tell it P, it can figure out Q. Right? So all it needs to know is how many, what's the probability of success, how many successes do you want. And it can do the rest. All it really does is that formula. It just plugs in into that formula. It just doesn't show you. So what do I want to put in here then? 30 people. Good. Comma. So I have punctuation on your calculator. Comma. P. Good. 11% chance of a left-hander. Comma. And I want 4, right? To compare with this guy. I want 4 left-handers. So 30 people, 11% chance of getting a left-hander. I want to get exactly 4 left-handers. Same damn number, thank God. Right? And of course it's the same number because the calculator just uses that formula, just populates it for you. Okay. Cool. See people just staring at the clock. That does not make it go faster. Sorry. I love that. Yeah. All right, so how do I check this then? How do I check this work? This work that took frickin' forever. CDF. And in fact, CDF always goes from 0 up to the number you put in. So in this case, I'm going to do binomial CDF 30, comma, 0.11, comma, 5, because I want to go up to 5. So let's try that out. So I got to go back to second vars, get to binomial CDF now, because I want a range. There's still 30 people, still 11% chance, but now I want to go up to 5. CDF is going to add them all together for me, and I get the same damn thing we got. You with me? That is, now of course this is where students disagree with me, but I don't care. I'm the teacher, I told you. This is not good enough for work. Don't just copy this down. The calculator is hiding what it's doing. This is a great way to check your work. Right? It's pretty easy. Great way to check your work. Not work itself. Cool. I got to see that. Okay, good. Because I always get people, I'm like, I wrote my work. No, you didn't. It's not working. Yeah.
You want to go up to like, all the way up to like 20 or something.
I won't make you by hand do, I wouldn't even make you do that much. At the most, I'd make you do 3 calculations. Because at that point, after that, it's really just busy work. All right? Okay, and that's crazy. I only have 80 people, 50 of them. No, that's easy. Yeah. Okay.
It's also really, really, really small numbers.
Depending.
Just kidding.
I think maybe I'll leave it there just in case. So here's that's section 5.3. Section 5.3 is all about that formula. Here's section 5.4. Section 5.4 is beautiful. Every time, let's take us back through time here. Every time we get a new way of giving data, what do we have to do? We have to figure out how to calculate the average and standard deviation. If I can get those 2 numbers, those are the best numbers at summarizing my data for somebody. So when we had a list of data, we had chapter 3 in the beautiful standard deviation tables, which you don't have to do anymore. Then we did XP of X. And we had its own formula, right? Mean is sum of XP of X, standard deviation, blah, blah, blah. These are the most beautiful little equations yet. Very little work. And I can explain the mean one. And the standard deviation one I'm just going to give you because the math proof is a little ugly for this class. Right? The mean one makes total sense. In fact, we already did it. If there are 30 people and an 11% chance of left-handed, how many would I expect? Expected value, which is another name for, what's the expected value another name for? EXP, another name for the average. The mean, right? What do you guys tell me? How many would you expect? How did you calculate it? Yeah, you took 11% of 30. I was like, well, duh. Of course you would. 11% of everybody's left-handed. You got 30 people. I expect 11% of them to be left-handed. You're like, holy shit, so that actually is something? Yes, that actually is. And we got like 3.3. That is the mean. Because that's the expected value. That's the average. So in general, the mean is just going to be, this is n, and this is p. That is the most kick-ass formula yet. Normally I pick on, the last couple of years I've had trouble because I used to always pick on Shaquille O'Neal. And then it became a Celtic. and then I had trouble picking on him, right? Picked on him basically because he was a Laker, and Lakers suck. But we'll see what happens. So if Shaquille O'Neal makes 30% of his free throws, right? And nowadays he could be doing them wherever he wants. If he makes 30% of his free throws and he takes 20 free throws, how many would you expect him to make? 6. 30% of 20 is 6. So that's another, that's what he would make on average. Would you be freaked out if he made 8? Would you be freaked out if he made 3? Would you be freaked out if he made 19? A little bit, right? You're like, whoa, that was a really good stretch for you. You kind of with me? What does that relate to? The whole, would you be freaked out here or there? What does that relate to that we've talked about in the past?
Unusual.
Yes, and what is the definition of unusual? Where does that start?
True standard deviation.
Beautiful. So we still have to calculate what the standard deviation is. So this one you're just going to have to take them. The variance is NPQ. That is definitely the best freaking formula for standard deviation yet. Well, to get the standard deviation, what would I do? Square root. Square root of NPQ. And that kicks major ass. So let's look at this Shaquille O'Neal problem again. And by the way, a few summers ago when the Celtics won the championship, I had some Lakers fans and I made a test. I had it all in green, had the Celtics logo on the top. And they said, I can't write on this. I said, you'll get an F then. And so, I enjoyed that. 15 years of failure. Oh. So if Shaquille makes 30% of his free throws, and he takes 20 free throws, the mean we just did already, that'll be 20 times 0.3 is 6. What's the standard deviation? Yeah, what's Q going to be?
0.7.
In this case, N is 20, P is 0.3. Q has got to be the rest. If P is success, Q is failure. P is make a free throw, Q is miss a free throw. That's got to be 0.7. The rest, 70%.
So the deviation is 2.05.
So square root of NPQ. What's the square root of 20 times 0.3 times 0.7?
2.05.
Sounds about right. Be careful now. 2.05.
2.0493494.
So never forget that standard deviation. I don't care where the hell it comes from. Always at least 3 decimal places. 4.3.
Do we go out for?
Oh, at least 3 decimal places. Yeah, I don't like to directly refer to sig figs. You only have to do that if you go into chemistry or something like that. So, what would be the minimum and maximum expected free throws he would make out of 20 then? How would you get that range? What did you say earlier? Unusual starts when you get how far out? 2 steps out. So you're going to do something that looks very familiar. Here's 6. That's what he makes on average. What's 2 steps up from there? So add that twice. Almost 10.1, right? And what's 2 steps down? Are you guys cool with that? You guys with me? This is add 2.049. Add another 2.049. 2 steps up. 2 steps down would be, what would it be? 3.9, roughly?
It's going to be
No, it's going to be
1.9.
1.90.
Yeah, 1 point. Went the wrong way. So would you be freaked out if Shaquille made 2 free throws? Would that be unusual? No. If he made 1 free throw, would that be unusual? Yes, that would be unusually a low amount. If he made 11 free throws, that would be an unusually large amount. Are you guys with me? Now again, nothing in statistics is hard set. People often think like independence doesn't mean that one has to happen for the other to happen. It just means it's going to change the chance that the other one happens. People always get that mixed up. Here, if he makes 11, is the universe falling apart? No, there's still how big of a chance? Let me see who can do this. How big of a chance is there for him to make something up down there or up here? What's the probability? Roughly.
3.03.
Roughly 5%. This is not perfectly normal, but it's pretty close. And then what percentage is within 2 steps? 95%. So roughly 5%. It's not perfectly normal, but that's a good rough estimate. You guys sort of with me here. I mean, that's why we define that to be unusual, because 5% is starting to get pretty rare. Right? We'll see in chapter 8, we'll start to be a little flexible with that, because why does unusual have to start at 5%? If there's a 7% chance of something happening, wouldn't you say that that's kind of unusual too? It all depends. So in chapter 8, we'll have a little more flexibility about where does unusual really start. Okay. That's 5-4. Believe it or not, I don't want to say things that make it sound like we're leaving because we're not. But 5-4, that's all there is in 5-4 is the mean, the standard deviation, and then max and min usual value. Then they'll ask you, is this usual? Is this unusual? Not a big deal. Who cares? I can just look at it. Does it fall in there or not? Not a big deal. Okay. So, what I'm going to try to do with the last bit of time we have left is I'm going to try to bridge the gap. I don't know if you guys remember, I think I made this point. Chapter 6 is really the most important chapter in this class. Because everything after that is based on the ideas in chapter 6. So, this is my attempt to show you how chapter 5 leads us into the idea of chapter 6.